Smokeless powder is the name given to a number of propellants used in firearms and artillery that produce negligible smoke when fired. Unlike the black powder they replaced, the term is unique to the United States and is generally not used in other English-speaking countries, which initially used proprietary names such as Ballistite and Cordite but gradually shifted to propellant as the generic term. The basis of the term smokeless is that the combustion products are mainly gaseous, compared to around 55% solid products for black powder. Despite its name, smokeless powder is not completely free of smoke. While there may be little noticeable smoke from small arms ammunition, smoke from artillery fire can be substantial. This article focuses on nitrocellulose formulations, but the term smokeless powder was also used to describe various picrate mixtures with nitrate, chlorate, or dichromate oxidizes during the late 19th century, before the advantages of nitrocellulose became evident. Since the 14th century, gunpowder was not actually a physical powder, and smokeless powder can be produced only as a pelletized or extruded granular material. Smokeless powder allowed the development of modern semi- and fully automatic firearms and lighter breeches and barrels for artillery. Burnt black powder leaves a thick, heavy fouling that is hygroscopic and causes rusting of the barrel. The fouling left by smokeless powder exhibits none of these properties. This makes an auto-loading firearm with many moving parts feasible. Smokeless powders are classified as typically Division 1.3 explosives under the UN Recommendations on the Transportation of Dangerous Goods, Model Regulations, Regional Regulations and National Regulations. However, they are used as solid propellants. In normal use, they undergo deflagration rather than detonation. Background: before the widespread introduction of smokeless powder, the use of black powder caused many problems on the battlefield. Military commanders since the Napoleonic Wars reported difficulty with giving orders on a battlefield obscured by the smoke of firing. Verbal commands could not be heard above the noise of the guns, and visual signals could not be seen through the thick smoke from the gunpowder used by the guns, unless there was a strong wind. After a few shots, soldiers using black powder ammunition would have the view obscured by a huge cloud of smoke. Snipers or other concealed shooters were given away by a cloud of smoke over the firing position. Black powder is also corrosive, making cleaning mandatory after every use. Likewise, black powder's tendency to produce severe fouling caused actions to jam and often made reloading difficult. Nitroglycerin and gun cotton. Nitroglycerin was synthesized by the Italian chemist Ascanio Sobrero in 1847. It was subsequently developed and manufactured by Alfred Nobel as an industrial explosive, but even then it was unsuitable as a propellant. Despite its energetic and smokeless qualities, it detonates instead of deflagrating smoothly, making it more liable to shattering a gun than propelling a projectile out of it. Nitroglycerin is also highly unstable, making it unfit to be carried in battlefield conditions. A major step forward was the discovery of gun cotton, a nitrocellulose-based material, by German chemist Christian Friedrich Schobein in 1846. He promoted its use as a blasting explosive and sold manufacturing rights to the Austrian Empire. Gun cotton was more powerful than gunpowder, but at the same time was once again somewhat more unstable. John Taylor obtained an English patent for gun cotton, and John Hall and Amp Sons began manufacture in Faversham. English interest languished after an explosion destroyed the Faversham factory in 1847. Austrian Baron Wilhelm Lenk von Wolfsburg built 2 gun cotton plants producing artillery propellant, but it too was dangerous under field conditions, and guns that could fire thousands of rounds using gunpowder would reach the end of the service life after only a few hundred shots with the more powerful gun cotton. Small arms could not withstand the pressures generated by gun cotton at all. After one of the Austrian factories blew up in 1862, Thomas Prentice and Amp Company began manufacturing gun cotton in Stowmarket in 1863, and British War Office chemist Sir Frederick Abel began thorough research at Waltham Abbey Royal Gunpowder Mills, leading to a manufacturing process that eliminated the impurities in nitrocellulose, making it safer to produce and a stable product safer to handle. Abel patented this process in 1865 when the second Austrian gun cotton factory exploded. After the Stowmarket factory exploded in 1871, Waltham Abbey began production of gun cotton for torpedo and mine warheads. Propellant Improvements. In 1863, Prussian artillery captain Johann F. E. Schultz patented a small arms propellant of nitrated hardwood impregnated with saltpeter or barium nitrate. Prentice received an 1866 patent for a sporting powder of nitrated paper manufactured at Stowmarket, but ballistic uniformity suffered as the paper absorbed atmospheric moisture. In 1871, Frederick Volkmann received an Austrian patent for a colloided version of Schultz powder called Colloidin, which he manufactured near Vienna for use in sporting firearms. Austrian patents were not published at the time, and the Austrian Empire considered the operation a violation of the government monopoly on explosives manufacture and closed the Volkmann factory in 1875. In 1882, the explosives company at Stowmarket patented an improved formulation of nitrated cotton gelatinized by ether alcohol with nitrates of potassium and barium. These propellants were suitable for shotguns but not rifles, because rifling results in resistance to a smooth expansion of the gas, which is reduced in smoothbore shotguns. In 1884, Paul Vier invented a smokeless powder called powder.B made from 68.2% insoluble nitrocellulose, 29.8% soluble nitrocellulose gelatinized with ether and 2% paraffin. This was adopted for the Lebel rifle. It was passed through rollers to form paper-thin sheets, which were cut into flakes of the desired size. The resulting propellant, today known as pyrocellulose, contains somewhat less nitrogen than gun cotton and is less volatile. A particularly good feature of the propellant is that it will not detonate unless it is compressed, making it very safe to handle under normal conditions. Vier's powder revolutionized the effectiveness of small guns because it gave off almost no smoke and was 3 times more powerful than black powder. Higher muzzle velocity meant a flatter trajectory and less wind drift and bullet drop, making 1,000 meter shots practicable. Since less powder was needed to propel a bullet, the cartridge could be made smaller and lighter. This allowed troops to carry more ammunition for the same weight. Also, it would burn even when wet. Black powder ammunition had to be kept dry and was almost always stored and transported in watertight cartridges. Other European countries swiftly followed and started using their own versions of powder.B, the first being Germany and Austria, which introduced new weapons in 1888. Subsequently, powder.B was modified several times with various compounds being added and removed. Krupp began adding diphenylamine as a stabilizer in 1888. Meanwhile, in 1887, Alfred Nobel obtained an English patent for a smokeless gunpowder he called Ballistite. In this propellant, the fibrous structure of cotton was destroyed by a nitroglycerin solution instead of a solvent. In England in 1889, a similar powder was patented by Hiram Maxim, and in the United States in 1890 by Hudson Maxim. Ballistite was patented in the United States in 1891. The Germans adopted ballistite for naval use in 1898, calling it WPC-98. The Italians adopted it as phyllite in cord instead of flake form, but realizing its drawbacks changed to a formulation with nitroglycerin they called solanite. In 1891 the Russians tasked the chemist Mendeleev with finding a suitable propellant. He created nitrocellulose gelatinized by ether alcohol, which produced more nitrogen and more uniform colloidal structure than the French use of nitrocottons in powder-B. He called it biocolloidin. Britain conducted trials on all the various types of propellant brought to their attention, but were dissatisfied with them all and sought something superior to all existing types. In 1889, Sir Frederick Abel, James Stewart and Dr. W. Kellner patented a new formulation that was manufactured at the Royal Gunpowder Factory at Waltham Abbey. It entered British service in 1891 as Cordite Mark Chapter 1. Its main composition was 58% nitroglycerin, 37% gun cotton and 3% mineral jelly. A modified version, Cordite MD, entered service in 1901. This increased gun cotton to 65% and reduced nitroglycerin to 30%. This change reduced the combustion temperature and hence erosion and barrel wear. Cordite's advantages over gunpowder were reduced maximum pressure in the chamber but longer high pressure. Cordite could be made in any desired shape or size. The creation of Cordite led to a lengthy court battle between Nobel, Maxim, and another inventor over alleged British patent infringement. The Anglo-American Explosives Company began manufacturing its shotgun powder in Oakland, New Jersey in 1890. DuPont began producing gun cotton at Carneys Point Township, New Jersey in 1891. Charles E. Munro of the Naval Torpedo Station in Newport, Rhode Island patented a formulation of gun cotton colloided with nitrobenzene, called Indurite. In 1891, several United States firms began producing smokeless powder when Winchester Repeating Arms Company started loading sporting cartridges with Explosives Company powder in 1893. California Powder Works began producing a mixture of nitroglycerin and nitrocellulose with ammonium picrate as patent powder. Leonard's Smokeless Powder Company began producing nitroglycerin nitrocellulose ruby powders. Laflin and Amp Rand negotiated a license to produce ballistite, and DuPont started producing smokeless shotgun powder. The United States Army evaluated 25 varieties of smokeless powder and selected ruby and patent powders as the most suitable for use in the Krag-Jurgensen service rifle. Ruby was preferred because tin plating was required to protect brass cartridge cases from picric acid in the patent powder, rather than paying the required royalties for ballistite. Laflin and Amp Rand financed Leonard's reorganization as the American Smokeless Powder Company. United States Army Lieutenant Whistler assisted American Smokeless Powder Company Factory Superintendent Aspinwall in formulating an improved powder, named WA for their efforts. WA smokeless powder was the standard for United States military service rifles from 1897 until 1908. In 1897, United States Navy Lieutenant John Bernadou patented a nitrocellulose powder colloided with ether alcohol. The Navy licensed or sold patents for this formulation to DuPont and the California Powder Works while retaining manufacturing rights for the Naval Powder Factory, Indian Head, Maryland constructed in 1900. The United States Army adopted the Navy single-base formulation in 1908 and began manufacture at Picatinny Arsenal. By that time Laflin and Amp Rand had taken over the American Powder Company to protect their investment, and Laflin and Amp Rand had been purchased by DuPont in 1902. Upon securing a 99-year lease of the explosives company in 1903, DuPont enjoyed use of all significant smokeless powder patents in the United States, and was able to optimize production of smokeless powder. When government antitrust action forced divestiture in 1912, DuPont retained the nitrocellulose smokeless powder formulations used by the United States military and released the double-base formulations used in sporting ammunition to the reorganized Hercules Powder Company. These newer propellants were more stable and thus safer to handle than powder-B, and also more powerful chemical formulations. Currently, propellants using nitrocellulose as the sole explosive propellant ingredient are described as single-base powder. Propellants mixtures containing nitrocellulose and nitroglycerin as explosive propellant ingredients are known as double-base powder. During the 1930s, triple-base propellant containing nitrocellulose, nitroglycerin, and a substantial quantity of nitroguanidine as explosive propellant ingredients was developed. These propellant mixtures have reduced flash and flame temperature without sacrificing chamber pressure compared to single and double-base propellants, albeit at the cost of more smoke. In practice, triple-base propellants are reserved mainly for large-caliber ammunition such as used in artillery and tank guns. During World War II it had some use by British artillery. After that war it became the standard propellant in all British large-caliber ammunition designs except small arms. Most Western nations, except the United States, followed a similar path. In the late 20th century, new propellant formulations started to appear. These are based on nitroguanidine and high explosives of the RDX type. Instability and stabilization. Nitrocellulose deteriorates with time, yielding acidic byproducts. Those byproducts catalyze the further deterioration, increasing its rate. The released heat, in case of bulk storage of the powder, or too large blocks of solid propellant, can cause self-ignition of the material. Single-base nitrocellulose propellants are hygroscopic and most susceptible to degradation. Double-base and triple-base propellants tend to deteriorate more slowly. To neutralize the decomposition products, which could otherwise cause corrosion of metals of the cartridges and gun barrels, calcium carbonate is added to some formulations. To prevent buildup of the deterioration products, stabilizers are added. Diphenylamine is one of the most common stabilizers used. Nitrated analogues of diphenylamine formed in the process of stabilizing decomposing powder are sometimes used as stabilizers themselves. The stabilizers are added in the amount of 0.5 to 2% of the total amount of the formulation. Higher amounts tend to degrade its ballistic properties. The amount of the stabilizer is depleted with time. Propellants in storage should be periodically tested for the amount of stabilizer remaining, as its depletion may lead to autoignition of the propellant. Physical variations. Smokeless powder may be corned into small spherical balls or extruded into cylinders or strips with many cross-sectional shapes using solvents such as ether. These extrusions can be cut into short or long pieces. Cannon powder has the largest pieces. The properties of the propellant are greatly influenced by the size and shape of its pieces. The specific surface area of the propellant influences the speed of burning, and the size and shape of the particles determine the specific surface area. By manipulation of the shape, it is possible to influence the burning rate and hence the rate at which pressure builds during combustion. Smokeless powder burns only on the surfaces of the pieces. Larger pieces burn more slowly, and the burn rate is further controlled by flame deterrent coatings that retard burning slightly. The intent is to regulate the burn rate so that a more or less constant pressure is exerted on the propelled projectile as long as it is in the barrel so as to obtain the highest velocity. The perforations stabilize the burn rate because as the outside burns inward, the inside is burning outward. Fast-burning pistol powders are made by extruding shapes with more area, such as flakes, or by flattening the spherical granules. Drying is usually performed under a vacuum. The solvents are condensed and recycled. The granules are also coated with graphite to prevent static electricity sparks from causing undesired ignitions. Faster burning propellants generate high temperatures and higher pressures, however they also increase wear on gun barrels. Smokeless propellant components. The propellant formulations may contain various energetic and auxiliary components. Propellants. Nitrocellulose, an energetic component of most smokeless propellants. Nitroglycerin, an energetic component of double base and triple base formulations. Nitroguanidine, a component of triple base formulations. Dina. Fivonite. DGN acetylcellulose. Deterrence. To slow the burning rate, centralites dibutyl phthalate dinitrotoluene acridite or thioetolylurethane. Polyester. Dipate camphor. Stabilizes. To prevent or slow down self-decomposition. Diphenylamine petroleum jelly. Calcium carbonate. Magnesium oxide. Sodium bicarbonate. Beta-naphthol methylethyramyl alcohol aniline. Decoppering additives. To hinder the buildup of copper residues from the gun barrel. Rifling tin metal and compounds. Bismuth metal and compounds. The bismuth compounds are favored as copper dissolves in molten bismuth, forming brittle and easily removable alloy. Lead foil and lead compounds, phased out due to toxicity. Flash reduces. To reduce the brightness of the muzzle flash. Potassium chloride, potassium nitrate, potassium sulfate, potassium hydrogen tartarate. Wear reduction additives. To lower the wear of the gun barrel liners. Wax, talc, titanium dioxide, polyurethane jackets over the powder bags in large guns. Other additives. Ethyl acetate, a solvent for manufacture of spherical powder. Rosin, a surfactant to hold the grain shape of spherical powder. Graphite, a lubricant to cover the grains and prevent them from sticking together, and to dissipate static electricity. Manufacturing. The United States Navy manufactured single-base tubular powder for naval artillery at Indian Head, Maryland. Beginning in 1900, similar procedures were used for United States Army production at Picatinny Arsenal beginning in 1907 and for manufacture of smaller-grained improved military rifle powders after 1914. Short fiber cotton linter was boiled in a solution of sodium hydroxide to remove vegetable waxes, and then dried before conversion to nitrocellulose by mixing with concentrated nitric and sulfuric acids. Nitrocellulose still resembles fibrous cotton at this point in the manufacturing process, and was typically identified as pyrocellulose because it would spontaneously ignite in air until unreacted acid was removed. The term gun cotton was also used, although some references identify gun cotton as a more extensively nitrated and refined product used in torpedo and mine warheads prior to use of TNT. Unreacted acid was removed from pyrocellulose pulp by a multi-stage draining and water washing process similar to that used in paper mills during production of chemical wood pulp. Pressurized alcohol removed remaining water from drained pyrocellulose prior to mixing with ether and diphenylamine. The mixture was then fed through press, extruding a long tubular cord formed to be cut into grains of the desired length. Alcohol and ether were then evaporated from green powder grains to a remaining solvent concentration between 3% for rifle powders and 7% for large artillery powder grains. Burning rate is inversely proportional to solvent concentration. Grains were coated with electrically conductive graphite to minimize generation of static electricity during subsequent blending. Lots containing more than 10 tons of powder grains were mixed through a tower arrangement of blending hoppers to minimize ballistic differences. Each blended lot was then subjected to testing to determine the correct loading charge for the desired performance. Military quantities of old smokeless powder were sometimes reworked into new lots of propellants. Through the 1920s, Fred Olson worked at Picatinny Arsenal experimenting with ways to salvage tons of single-base cannon powder manufactured for World War I. Dr. Olson was employed by Western Cartridge Company in 1929 and developed a process for manufacturing spherical smokeless powder by 1933. Reworked powder-washed pyrocellulose can be dissolved in ethyl acetate containing small quantities of desired stabilizers and other additives. The resultant syrup, combined with water and surfactants, can be heated and agitated in a pressurized container until the syrup forms an emulsion of small spherical globules of the desired size. Ethyl acetate distills off as pressure is slowly reduced to left small spheres of nitrocellulose and additives. The spheres can be subsequently modified by adding nitroglycerin to increase energy, flattening between rollers to a uniform minimum dimension, coating with phthalate deterrents to retard ignition, and or glazing with graphite to improve flow characteristics during blending. Modern smokeless powder is produced in the United States by St. Mark's Powder, Inc. owned by General Dynamics. Flashless propellant. Muzzle flash is the light emitted in the vicinity of the muzzle by the hot propellant gases and the chemical reactions that follow as the gases mix with the surrounding air. Before projectiles exit, a slight pre-flash may occur from gases leaking past the projectiles. Following muzzle exit, the heat of gases is usually sufficient to emit visible radiation. The primary flash. The gases expand, but as they pass through the mag disc they are recompressed to produce an intermediate flash. Hot combustible gases may follow when they mix with oxygen in the surrounding air to produce the secondary flash, the brightest. The secondary flash does not usually occur with small arms. Nitrocellulose contains insufficient oxygen to completely oxidize its carbon and hydrogen. The oxygen deficit is increased by addition of graphite and organic stabilizers. Products of combustion within the gun barrel include flammable gases like hydrogen and carbon monoxide. At high temperature, these flammable gases will ignite when turbulently mixed with atmospheric oxygen beyond the muzzle of the gun. During night engagements, the flash produced by ignition can reveal the location of the gun to enemy forces and cause temporary night blindness among the gun crew by photo-bleaching visual purple. Flash suppressors are commonly used on small arms to reduce the flash signature, but this approach is not practical for artillery. Artillery muzzle flash up to 150 feet from the muzzle has been observed, and can be reflected off clouds and be visible for distances up to 30 miles. For artillery, the most effective method is a propellant that produces a large proportion of inert nitrogen at relatively low temperatures that dilutes the combustible gases. Triple-based propellants are used for this because of the nitrogen in the nitrogen. Before the use of triple-based propellants, the usual method of flash reduction was to add inorganic salts like potassium chloride so the specific heat capacity might reduce the temperature of combustion gases and the finely divided particulate smoke might block visible wavelengths of radiant energy of combustion.